So let's do an example. And in this case, we're going to try to find the volume enclosed by these two surfaces. So our first step uh, is going to be to sketch the region and also to notice that we can write volume if it's between two surfaces, this one and this one, that is not just a surface bounded by the xy plane. So in this case, we're going to see in a minute that my bottom surface is not the xy plane. In that case, I'm going to need a triple integral. And in my integrand, I'm just going to have dv. And now I need to think of what my limits will be. So go ahead and sketch it for a minute, and you can show me how you realize that the bottom surface is not just the xy plane. Okay, so let's visualize this. I'm going to actually go up. Okay, here is the first surface. Z is x squared plus 3y squared. So this is the surface Z is x squared plus 3y squared, which is this elliptic paraboloid. And then the other surface is a circular paraboloid opening down. And so if we put them both together, we're really looking at the intersection of the two here. And so let's just sketch the intersection. There we go. So it's this kind of egg-shaped region that we should have gotten. Okay, and so now we're going to take this region. This is what we're trying to find the volume of. We're going to integrate over this, set up a triple integral that describes this region. So let's come back to this picture now and set up our bounds to find the volume. So first thing, we can just try the ordering dz, dy, dx. And so we're going to do our inside integral first. And that's holding x and y constant and just varying z. So this is my innermost one, and then we'll get, and when I'm finding the volume, my integrand is just going to be 1. So we're just going to get this all set up, and then we're going to find the bounds. Okay, so to find the innermost one, I'm freezing x and y, and I'm going to shoot an arrow parallel to the z-axis through my region. And I'm going to look at where that arrow would enter and where it would exit. So notice no matter where I choose to shoot this arrow, it's always entering along this bottom surface, which is an entire surface. It's coming from this entire elliptic paraboloid here, and it's always exiting along the top surface, which is that circular paraboloid. So my lower limit is going to be x squared plus 3y squared. My upper limit is 8 minus x squared minus y squared. And let's also just look at this one more visual. This is the same region, just sketched in a different app. And so notice what we're doing if I'm slicing, and we're just looking at the intersection, by the way, so just the shaded region of these two. But if I'm slicing with respect to z first, then I'm really just interested at what this height is, or really just interested at where this enters and exits the region here, this region of intersection, along different z arrows. And so that is my first bound, which is basically just going to be capturing this height. And then I can also move this and look, oh, I think that's not going to work here, but I could also shoot this along different x's and y's and still see what my little z arrow, where it would enter and where it exit. And no matter where I shoot it through this region, it's always entering along this bottom elliptic paraboloid and always exiting along the top. So those are my first two bounds. Okay, now to get the next bounds with respect to x and y, I need to look at the shadow of this region on the xy plane. And so let's look at it visually, and then we can see it's going to be this kind of shape. Let's look at it visually in Mathematica, and then we'll come back and find it analytically. Okay, so here we can see that the shadow is going to be, we come up to the very top of this object. Let's turn it around a little bit. There we go. So the shadow is going to be that elliptical region in the XY plane. And in this particular case, what's causing the shadow is the intersection of the two surfaces. And so I want to find where the two surfaces intersect, and that's going to give me the shadow on the XY plane. So to do that, let's set both of the surfaces equal to each other and find that ellipse of intersection. Okay, so to find the intersection, set these equal to each other. So go ahead and put this on pause and then see if you can get the equation for the ellipse that's their intersection. Okay, and we can write this in the standard equation of an ellipse if we divide both sides by 4. And that's going to give me my squared. Okay, so that means that this intercept right here is the square root of 4, and this intercept up on y is the square root of 2. All right, so now let's come up with our actual integral bounds here with respect. So if we're going to do the next integrate with respect to y, then we are going to imagine that we're shooting an arrow through this shadow region parallel to the y-axis, and we're going to look at where it enters and where it exits. So you notice it's always entering along the bottom half of the ellipse, and so I can solve the ellipse for y. It's probably easiest to solve this equation here because there will be less fractions involved. So when I solve this one for y, I am getting y is equal to negative square root of, wait, let's do actually, hold up. That one still is not simplified. Let's do this one. That one's nice and simplified. So y is negative square root of 4 minus x squared all over 2. And that's the lower limit. And then my upper limit is going to be the positive of that. So let's put that down here in my integrand, or in my integral limits, excuse me. And then lastly, I just want to figure out what are my x bounds. So those are going to be the largest and the smallest x values on this region. They're always constants. My outside limits are always constants. So that's just going to go from -2 to 2. And so now we're ready. And if you're looking at this thinking, oh man, this integral looks messy, you're right. But I can't, right now, there's not an obviously quick coordinate change that we could do, because switching to polar is, well, first of all, we don't know how to switch in coordinates, triple integrals yet. And then if I was going to switch to polar, I'd have to wait until I got to the double integral part. But polar isn't really going to help me with an elliptical region. So we're just going to do this one in Cartesian. And we're just going to start step by step. So I'd say put this on pause. This is going to get to be a messy integral. I'd say put it on pause and try the whole thing. And then I'm going to walk you through all the details on the next page after you've tried it. Okay, I warned you this is going to get messy. So first, you're going to integrate with respect to z. And that's going to get us, let's see if I can get my pointer. Here we go. Good. That's going to get us right here. And then I'm just plugging in the top bound right there and the bottom bound right here. And then I'm integrating this whole thing with respect to y. And so now I have, let's see, wait, where did that come from? Okay, I see now. This minus 2x squared, that's coming from the minus x squared and then minus this x squared here. And then minus y squared plus the 3y squared, and then we're going to integrate it. Okay, so we're integrating now. This is the integral with respect to y, and then we have these bounds. And now we're going to go plug in. And then this just looks messy, I agree. But I want you to notice a little trick. One of the tricks is I have this square root, or I have this quantity 4 minus x squared over 2 that keeps showing up everywhere. And so it would be great if I could rewrite this in terms of that. So notice 8 minus 2x squared is the same as pulling out 4 over 4 minus x squared. And then the 2, okay, I really skipped a step that I wanted you to see here. I pulled out this 2 here, and then I'm getting 4 minus x squared, and then I'm rewriting that 2 as 4 over 2. And that's how we end up back here. Okay, so I'm replacing everywhere I had an 8 minus 2x squared, and notice I have this whole term minus the negative of that term, so I'm just going to be adding it twice, which is what the red is right here. And then here is at 4 over 2, which is replacing this piece. And then this I have twice. I have this here, and then minus it again over here, so that's what the 2 is. Now I can just rewrite things in terms of this quantity 4 minus x squared over 2 to the 3 halves, combine them, and I end up with this. And now I'm still stuck. I can't do a U sub, can't do integration by parts, but I can do a trig sub. And so remember, if I want to do a trig sub with something of the form constant minus variable squared, then one option is to let my x be 2 sine theta. Dx is 2 cosine theta, d theta, and then I change variables. Okay, so then that's going to become, here's the 4 minus x squared to the 3 halves. It becomes this. The dx becomes this. And then I can just end up pulling out the 8 times the 2 times the 4, so that's giving me the 64. And I'm writing cosine to the 4th as cosine squared squared. And then this is another one of those integrals from Calc 2. If you have an even trig function squared, or excuse me, if you have cosine or sine squared, it's nice to use this half angle formula and rewrite it. So that's what I'm doing from there to there. And then I'm just foiling that out, and we're left with this. And I'm going to need to use, I can integrate the first 2 terms, no problem. So that's what's happening here and here. Then I'm going to need to use the half angle formula or double angle formula again here to rewrite this as 1 plus cosine 4 theta over 2. I know this is messy. I wanted to show you that I'll walk you through one where it gets really nasty and you have to use a bunch of your Calc 2 integral techniques. And then we're just evaluating these. Let's see, yep. And we're going to end up finally at the end of the day with 8 pi square root of 2, which as a reminder is the volume of that little egg shape that we were trying to find.